Hi, my name is Yuriko Benedict. Registration number 210160022. Today I'm going to explain about how my group 19 did the advanced objective. First, we start with this function over here. This is the sensor input function. This line over here uh, calls for the microcontroller to start converting the value from the infrared sensors in front. Well, we are just using one of them because we don't need both to do obstacle avoidance. This waits for it to be done, and this returns the value from both the lower and the higher memory chip from the microcontroller. We need both memory chips because the output is 10 bits and the memory only saves up to 8 bits. So this output will be used in the in the obstacle avoidance, which is in the FTL function. In our case, we didn't feel the need to create a new function because it wasn't that long and it's both related to the movement of the robot. So here's the actual FTL function itself. And there's a lot of inputs for the FTL function, but the only actual input we need for the obstacle avoidance is this one, the max speed input. See, this section over here is the actual obstacle avoidance. So the max speed itself is the desired speed that the user wants the robot to move in. Let's say we want the robot to move in half the theoretical maximum speed. We'll put it's around 500, and the theoretical maximum input for the motor is 1023. So we take 1023 divided by the max speed, we get the ratio Z, which is used because the input from the sensor will be in a constant scale, which is 0 to 1023, and it is inverse to the motor. So we figured, instead of doing a bunch of ifs, we could just use 1023 deducted by the input of the sensor. That will be the output of the motor, which if it's close, it'll be 1023. When it's further, it'll be less, up to 0. So whenever, let's say the input is 500 and the maximum speed of the motor is 1023, when we deduct it, it'll be 500, so it'll be half the speed because it's half the maximum distance. But since we know that we will not run at the maximum speed of the motor, we use this ratio to compensate for that. The ratio will be used in the next line, which is the actual motor speed that we will input to the program below later after I explain this part. So maximum speed deducted by the sensor input divided by the ratio, which means whenever the sensor input, let's say the Z is 2, which is basically half the ratio. So even if the sensor inputs the maximum value, it'll be 0 essentially when the max speed is deducted by this. So the robot will stop. So let's say the maximum speed is 500, 512, let's say. So whenever 1023 is divided by 512, it will come to about 2. Even if the sensor input is 1023, it will be divided by 2 as well. So it will be the same value as the max speed. This will be outputted to m speed over here, which is used. See, this is the FTL function, which my teammate has probably explained in the other video. See, right, the FTL function outputs in U, which is the correction given to each motor depending on the error. But before that, there is m speed over here, which is the speed that is outputted by the obstacle avoidance. So even when it's doing obstacle avoidance, it will still do FTL. And there's an extra if logic we added here just in case, because the sensor is not 100% accurate. So we figured anything above 600 actual value of the sensor before being divided by the ratio. Anything higher than 600, which is about maybe 1.5 centimeters, the motor will be cut off just to avoid it crashing into anything, because we found out that anything closer than the 1 centimeters, the sensors are not that accurate anyways. So the operating range that we went for is from 0 to 600-ish. We see no problem during implementation. And that's it. That's how we did our advanced objective. Thank you.